All right, so I'm going to go back into section 4.3. We're going to do a couple more problems here. A couple more I'm going to touch base with here. Number 31. Okay, this involves blood types and RH factors. In addition to being grouped into 4 types, human blood is grouped by its races factor. Consider the figure below, which shows the distribution of these groups for Americans. Type O blood, A, B, or AB blood, and you could have an RH positive or RH negative factor here. All right. Now notice these are in percent, so I mean, you can think of it as being like 100 people were randomly surveyed, and 37 of the 100 had type O with RH positive blood. 34 had type A with RH positive blood. Only 1 person had AB blood with RH negative. Okay, so you can think of these as being numbers and just drop the percent, and we'll consider this to be a sample of size 100 or something, like that. All right, so okay, so what I want you to do is do a couple of these problems here. We'll open up with like classwork number 1. See if you can do like problems A through C here. We'll call this classwork 1 here. 31 A's through C. Given this table, see if we can answer these questions or determine these probabilities. Okay, go ahead and do those. Call that classwork 1. Again, the table's right up here. All right, so again, we're doing 31 A, B, and C for classwork 1 here, given this table regarding blood types. Okay, 31A is what's the probability that a person randomly selected from the sample size 100 is a universal donor? What that is to say that they are O negative blood. Well, O and type O and negative blood would be 6% right here, 6 on 100. So that's 0.06. So this probability should be 0.06. B, what's the probability that we select somebody and they have type O blood given that the person is Rh positive? Given that the person is Rh positive, basically locks us into the Rh positive row. So we're locked into this row. Given that the person selected is Rh positive, what then is the probability that they have type O blood? Well, we need a row total here. So we're going to compute this row total. We're going to have to add all these up, 37 plus 34 plus 10 plus 4. And so that's going to net us 71, 81, 85. Okay, so of 85 people that are RH positive, how many are type O? That'd be 37 over 85. So your answer would be 37 over 85. And as a fraction, excuse me, as a decimal, what's that going to be? That's going to be about 0.44. All right, so approximately a 0.44. So given that we select somebody that's Rh positive, the probability that they're type O blood will be about 44% chance. Again, that was found by taking 37 and dividing it by 85, which is the row total of Rh positive. All right. C, what's the probability somebody randomly selected has A positive or AB negative blood? So that's A positive. Hold on a second. Let me erase this here. Okay. Probability that person has A positive or AB negative. This is an OR probability, which means we're going to have to add these individual probabilities together. So we tap into an addition rule. So this is the probability. We select somebody that's A positive. Added to the probability, we select somebody that's AB negative. And the probability we select somebody that's A positive would be right here. That'd be 34 out of 100 or 0.34. And that's going to be added to the probability we select somebody that's AB negative. AB negative would be 1 out of 100, 0.01. So your answer to this problem is going to be about a 35% chance, 0.35. That's your answer. All right, 0.35. Okay, any questions about those? We'll call that classwork number 1. All right, classwork number 2. I would like you to do this one here. Using this data table here, which lists the numbers of doctors in various specialties by gender, I want you to answer questions A, B, and C. Okay, so 32 A, B, and C, we'll call this classwork number 2. All right, go ahead and do that. All right, let's take a look here for A. Is to be read. This is a conditional probability. You read it as, given that we select a pediatrician, what's the probability that that person's a male? Given that we select a pediatrician, locks us into the pediatrics column. So we're locked into this column here. Now, given that we're locked into that column, the pediatrician column, was the probability of selecting a male. There's 33,020 males out of 66,371 pediatricians. So your answer is going to be 33,020 divided by 66,371 is about 0.50. That's your answer for A. Did anybody get that?
Yep.
All right, next one. Given that we select a female, what's the probability that we select a pathologist? Well, given that we select a female, locks us into the female row. So we're locked into the female row here. So given that we're locked into the female row here, what's the probability we select a pathologist? Well, that's 5,604 divided by 51,247 females. So 5,604 pathologists divided by 51,247 females, 0.11. That's your probability, approximately about 0.11. Anybody get that? Now, C, are the characteristics of being a female and a pathologist independent of one another? Well, if they are independent, then this conditional probability, given that we select a female, that we select a pathologist, would have to be equivalent to the probability that we select a pathologist. Reason being is because if being female and a pathologist are independent, it doesn't matter if you select a male or a female. It's not going to affect the probability of whether you select a pathologist. Well, the problem is when you compute this conditional probability, given that we select a female, that we select a pathologist, okay, which is 0.11 according to the answer we got in part B up here, that's not equivalent to the probability of selecting a pathologist. The probability of selecting a pathologist is 18,179 divided by 124,645, which is 0.15. Because these probabilities are not equivalent to each other, we say that these events are not independent of each other. Not independent. All right. So that's classwork number 2. Okay, ladies and gentlemen, we can move on now. Let's get into section 4.4, where we're going to learn how to count. Now, believe it or not, you could kill a whole 15-week semester at a university just learning how to count. It's called a course in combinatorics, okay? We're not going to spend 15 weeks on learning how to count. We're just going to dip in and look at some of the highlights of combinatorics, some tools that we can then use to compute probabilities of more complicated compound events. All right, so counting. When we get done with this section, we'll learn how to find the total number of outcomes in a sequence of events using what's called the fundamental counting principle or counting rule. We'll also be able to find a number of ways that R objects can be selected from N objects using the permutation rule. And we'll also learn how to find a number of ways that R objects can be selected from N objects without regard to order, in which case we would use the combination rule. Okay. All right, the fundamental counting principle or the fundamental counting rule here. All right, basically the fundamental counting rule says that in a sequence of n events, in which case the first event has k sub 1 possibilities of occurring, and the second event has k sub 2 possibilities of occurring, and the third event has k sub 3 possibilities occurring, and so forth, then the total number of possible arrangements in a particular sequence of these events can be computed by multiplying the individual possibilities of each simple event together. Okay, so this is called the fundamental counting principle, or the fundamental counting rule here, right? And this fundamental counting rule is going to enable us to compute more complicated probabilities that we were unable to compute in the previous sections. All right, let's see if we can look at an example here. Suppose a coin is tossed and then a die is rolled. How many outcomes are there for this sequence of events? Well, they have a tree here to enumerate all the possible outcomes that could occur. When you roll a coin, two possible outcomes could transpire. Either you flip a tail or heads. And when you roll a die, either you're going to roll a 1, 2, 3, 4, 5, or 6. So there's two possible ways in which the first event can occur, that is flipping a coin. And there's 6 possible outcomes or ways in which to roll a die. Therefore, the total number of possible combinations, if you will, or arrangements between flipping a coin and rolling a die, according to fundamental counting principle, is going to be 2 times 6, or 12. So there's going to be 12 possible ways or outcomes, if you will, of flipping a coin and rolling a die. And here's the 12 possible ways. You could flip a head and roll a 1, a head and a 2, head or 3, head or 4, head or 5, head or 6, tail or 1, tail or 2, tail or 3, tail or 4, tail or 5, tail or 6. Those are the 12 possible outcomes that could occur. So that's making use of the fundamental principle of counting here. Okay. 12 possible outcomes. And this tree diagram helps us to actually see what the 12 outcomes are. All right. Now, when we enumerate possible outcomes, or we actually get into counting, we're going to need a function to help us out. It's called the factorial function. Okay. Suppose if you look at a standard deck of cards, if we reach in and pull out a card and we return each card to the deck after we draw it, there are 52 possible outcomes for every draw. However, if we do not return the card to the deck every time, the number of possibilities, of course, decreases every trial of the experiment of selecting a card from the deck. So in that case, there will be 52 possible outcomes on the first draw, but only 51 possible outcomes on the second draw, and 50 outcomes on the third draw, and 49 outcomes on the fourth draw, et cetera, et cetera, et cetera. So if repetitions are permitted, the numbers are the same going from left to right. If repetitions are not permitted, the numbers decrease by 1 for each place left to right. Suppose that we have a pile of 5 cards and we draw each one in turn. The number of possibilities are going to be 5 times 4 times 3 times 2 times 1. If there had been 7 cards in the pile, then the number of possibilities would then have been 7 times 6 times 5 times 4 times 3 times 2 times 1 way of drawing these 7 cards here. This product here is called a factorial. All right. And we call 5 times 4 times 3 times 2 times 1, we call that 5 factorial. And that's represented symbolically as as 5 with this exclamation symbol here. So we read this as 5 factorial in mathematics. In general, n factorial is going to be n times n minus 1 times n minus 2 times n minus 3 times n minus 4 times ... all the way down till we get to 3 times 2 times 1. Okay. Oddly enough, 0 factorial is defined to be equal to 1. 0 factorial is not 0, it's equal to 1. And a way to maybe reconcile a reason why this is suppose that we have 0 cards in a pile. Well, there is only one possibility if you draw all the cards from the deck. The case where you have no cards. All right. 0 cards in a pile. There's only one possibility. If you draw all cards from the deck, the case would be where we have no cards. All right. All right, a permutation. What is a permutation? It's an arrangement of n objects in a specific order. Now, the key with permutations is that order does matter, all right? Unlike combinations where order does not matter. Suppose we want to arrange 4 people in a line for a family photograph. We have 4 choices for the person on the left, 3 choices for the next person, 2 choices for the third person, on and on down the line to 1 choice for the last person. In other words, there are 4 factorial, or there would be 4 times 3 times 2 times 1 ways of arranging these 4 people in line in a specific order. There would be 24 possible arrangements here. Okay. 24 different ways of arranging these 4 people in a specific order. Now, the number of permutations of n objects, therefore, is n factorial, equal to n factorial. What if we had a class of 20 students and we wanted to arrange 3 of them to answer 3 questions in front of the rest of the class? Now, we have 20 choices for the first student to choose from. But if we select a student from the 20 and keep that student out, then we only have 19 choices to make the second selection. If we keep that second student out, therefore we only have 18 choices to make the third selection. So there's 20 times 19 times 18 different ways of selecting 3 students from 20 students in a particular order. And 20 times 19 times 18, is going to be a sizable number here. So there would be 6,840 different ways of choosing 3 students from 20 students in a particular order. A lot of different possible ways. We're not going to enumerate all those ways. We'll be here forever. But notice 20 times 19 times 18 is really equal to this. 20 times 19 times 18 times 17 times 16 times 15 times 14 times 13 times ... all the way down to 2 times 1, divided by 17 times 16 times 15 times 14 times 13 times ... times 2 times 1. Notice the 17 on down to times 1 all drops out, cancels out. And what we're left with is 20 times 19 times 18. So as it turns out here, we can see that 20 times 19 times 18 is really equal to this, 20 factorial divided by 17 factorial. Well, this is called a permutation of 20 objects taking 3 objects at a time. And symbolically, it's denoted this way. This is a symbolism that represents a permutation. Okay, 20 objects permuted 3 ways, or 20 objects taking 3 objects at a time in a particular order. That's how you read this notation here. Now, there is a formula for computing a permutation of n things permuted r ways. And this is the formula. It makes use of the factorial function. So n permuted r ways would be n factorial divided by n minus r factorial. So if you look at our problem up here, 20 permuted 3 ways, that's going to be equal to 20 factorial divided by 20 minus 3, which is 17 factorial. 20 factorial divided by 17 factorial. Now, on our calculator, our TI-84 calculator, we do have the factorial function at our disposal. To access it, you'd have to hit the math button, go over to probability, whoops, and then you go down and there's your factorial function. To show you how it works, 4 factorial would be 4 times 3 times 2 times 1, which would be 24. We type in 4, hit your math button, go over to probability, go down and grab the factorial function, and hit enter, and you get 24, 4 factorial. So using this permutation formula here, which involves the factorial function, we can, compute a permutation. But there's an even quicker way, ladies and gentlemen. The quicker way is in math probability, we also have our permutation function built in, n permuted our ways. So if you look at our example, 20 permuted 3 ways, okay? The number of ways we can select 3 students from 20 students in a particular order. We can compute that on our calculator. First, we type in n, which is 20. Math, go over to probability, go down and grab the permutation function, NPR. And now you got to type in R, which is 3. Hit enter, and you get 6,840 different ways of choosing 3 students from 20 students in a particular order, where order does matter. Okay, that's called a permutation. So in other words, you could select Johnny, Sue, and Jill, or you could select Jill, Sue, and Johnny, or you could select Sue, Johnny, and Jill. Those are all different selections because the order is different in each case. There's 6,840 different ways of selecting 3 students, 3 different students, okay, from 20 students in a particular order. That's called a permutation. All right, permutation rule number 2. The first permutation rule, the one we just seen here, n permuted R ways, this formula here, only is valid if all the items are different. And in our example on the previous slide, all of the students were not the same. They were all different. They're all unique. However, ladies and gentlemen, if some of the items are the same, we're going to have to use the second permutation rule. Okay. For example, how many permutations are there of the letters of Mississippi? In other words, how many unique different ways can we arrange the letters in the word Mississippi? Well, one way to arrange these letters is to have them in the order that we see. But ladies and gentlemen, suppose that I interchange these 2 S's. Okay. Well, if we interchange these 2 S's, we would still have the same word, Mississippi. All right. So that's redundant. And so therefore, because we have repeated S's in here, all right, we're going to have to reduce the total number of different arrangements of these letters in order to compute the number of ways these letters can be permuted in a specific order. Right? Notice we not only have repeated S's, but we also have repeated I's and P's. All right. So therefore, the total number of ways of arranging, okay, these letters in the word Mississippi and having a unique word or a unique arrangement is going to be equal to the total number of letters in the word Mississippi, which is n, and that'll be n factorial. So how many letters are there in the word Mississippi? There's 11 letters. But 4 I's are identical, and 4 S's are identical, and 2 P's are identical. And there's only 1 M. Therefore, the total number of permutations of the letters in the word Mississippi that would form unique arrangements in a particular order is going to be equal to 11 factorial divided by 4 factorial times 4 factorial, because there's 4 I's and 4 S's, times 2 factorial, because there's 2 P's, times 1 factorial, 1 because there's only 1 M. And when you do this, dial this up on your calculator, you would get the result that they have here. And let's show you how to do this on the calculator quickly. So we would have 11, and we got to go get the factorial function. So math, probability, function number 4 here. 11 factorial divided by an open, in a set of parentheses, I'm going to put 4 factorial. 4 math probability factorial times 4 factorial, 4 math probability function number 4 times 2 factorial, 2 math probability factorial function. You know, 2 factorial is just 2 times 1 is 2. So, I mean, you could have just typed in 2 here. 1 factorial is just 1. Just type in 1. All right. That's how you type it in on your calculator. And you do get 34,650 unique ways of arranging these letters in the word Mississippi to form a unique arrangement in a particular order. Okay. Now, we're obviously not going to enumerate all the ways or show you all the ways. We'll be here for a very long time. All right. Permutations. Order matters with permutations. Okay. So let me just expound upon that real quickly if I could here. Suppose that you have sorry here. Suppose you have 3 people. You have Jill, you have Hector, and you have Bo. All right. If I wanted to form, let's say, I wanted to select 2 people from this group. One person is going to take the office of president, and the other person is going to take the office of vice president. Does order matter here, do you think? Does order matter in how I select these 2 people? President versus vice president.
Yes.
Yes, order is going to matter here. So one way to form a cabinet is I could select Jill as president and Hector as vice president, or I could select Hector as president and Jill as vice president. These are not the same. They're different because order matters. Order matters. I could select Jill and Bo, or Bo and Jill, or I could select Hector and Bo, or Bo and Hector. There's 6 possible ways of forming my cabinet of president and vice president if order matters, if I have those 3 people to choose from. Is that making sense there? Or order matters? Now, ladies and gentlemen, since order matters, this is a permutation. So to determine the 6 possible ways or 6 arrangements here, or the total number of arrangements, which is 6, we speak in terms of a permutation. So we have 3 people that we want to permute 2 ways. So in other words, we want to try to determine how many ways we can select 2 people from 3 people if order matters. 3 permuted 2 ways. Well, if you use the formula, it's going to be 3 factorial divided by 3 minus 2 factorial. You could do it the long way, or you could just use your calculator and use your NPR function. So how would we do this on our calculator if we wanted to use the NPR function if we did not want to use the factorial here? If you use the factorial, 3 factorial is 3 times 2 times 1. 3 minus 2 is 1, and 1 factorial is 1. 3 times 2 times 1 is 6 over 1 is 6, or 6 ways of selecting 2 people from 3 if order matters. And we've enumerated the 6 possible arrangements here. Or you get on your calculator and use your NPR function. Type in 3, go get NPR, type in 2, hit enter, and you should get 6. Okay? Any questions about a permutation or order matters? All right, I have a question for you, Liz. What if order does not? What if order does not matter? What if instead of selecting 2 people from these 3 people to form a political cabinet, suppose we don't care about that anymore. Suppose we're trying to figure out, okay, how to select two people from these three people to form, let's say, a tennis team. I have a question for you. If we're trying to form a tennis team of size 2 from these three people, do you think order matters in how we select these people, these two people?
No.
Doesn't matter at all. It doesn't matter if we select Jill first and Hector, or if we select Hector first and then Jill. We have the same team, Jill and Hector, or Hector and Jill. Order does not matter. If order does not matter, how many different ways can I select two people from three if order does not matter? Jill and Hector could be on my tennis team, or Hector and Jill. But Hector and Jill on my tennis team is the same as the team of Jill and Hector. We get rid of this guy. That's redundant. That's a repeat. We only count this team once. I can select Jill and Bo to be on the tennis team, but that's the same as Bo and Jill. Get rid of that. I could select Hector and Bo, but that's the same team as Bo and Hector. Get rid of this. There's only 3 ways of forming a tennis team of size 2 from 3 people if order does not matter. Ladies and gentlemen, that's called the combination. Not a permutation, but a combination. So permutation, order matters. Combination, order does not matter. Okay? So the number of combinations of R objects selected from N objects is denoted symbolically as NCR. And the formula for a combination is N factorial divided by R factorial times N minus R factorial. What's the difference between this formula for a combination and the formula for a permutation? What's the difference? Whoops, here we go. What's the difference between these formulas? Here's a permutation formula. And here is the combination formula. There's only one difference. What is it?
You're multiplying the denominator by R factorial.
Yep, we have another factor appearing on our denominator, which is R factorial. And because of that, think about it. Is the denominator of a combination going to be larger or smaller than the denominator of a permutation? Permutation doesn't have this extra factor. So again, is the denominator for a combination going to be larger or smaller than that of a permutation? What do you think?
Larger.
Larger. And because the denominator of a combination is larger than the denominator for a permutation, this fraction is going to be smaller than the fraction or the ratio for a permutation. The bottom line is this, ladies and gentlemen, combinations are always less than permutations because of that reason. So N in combination with R is less than N permuted R ways. Okay? That's always true. All right, now, suppose we want to choose 3 people from a group of 8 people where order does not matter. You know, maybe we want to form, I don't know, what sport has 3 people? Maybe a golf team. We want to form a golf team of size 3 from 8 people where order doesn't matter, in which we select the people, the players. Well, that's called a combination. So 8 in combination with 3 would be 8 factorial divided by 5 factorial times 3 factorial. Now, what is 8 factorial? You know, 8 factorial can be written as 8 times 7 times 6 times 5 factorial. Because 5 factorial is 5 times 4 times 3 times 2 times 1. So 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 would be 8 factorial. Why did they write 8 factorial as 8 times 7 times 6 times factorial? Because this 5 factorial in the numerator is going to cancel out with the 5 factorial in the denominator. That's why they stopped it there for 8 factorial. So, but what's 3 factorial? 3 factorial is 3 times 2 times 1, which is 6. So 3 factorial cancels out with the 6. So you know what? The total number of ways of selecting 3 people from 8 people where order does not matter is 56 different ways. 8 times 7, 56. Now, an easier way to have done this is to just use your calculator. 8 in combination with 3. You don't have to use the factorial business for the combination of the permutation. It's a lot quicker if you just, use the function directly. So 8 in combination with 3 is 8 math probability. Go down and grab the combination function, NCR. 8 in combination with 3. Enter, 56. So do we understand how to use our permutation or combination functions on our calculator? All right. Now I have a question. If order did matter, suppose that we're again trying to, form a political committee where we have a president, vice president, and maybe a treasurer. Would there be more or less than 56 ways of selecting 3 people from 8 people then to form the cabinet? What do you think?
More.
A lot more, right? If order matters. Okay, because Ben, Sue, and Harry would be different than Harry, Sue, and Ben. All right. But if order doesn't matter, there's only 56 ways of selecting 3 people from 8 people. All right, so hopefully we understand the difference between a permutation versus combination. Again, permutation order matters. Combination order does not matter. And usually it's pretty clear with your applications as to whether order is going to matter or not. Okay. All right, so we learned a couple of counting rules. Number 1, we learned the fundamental rule of counting. That is, if a first event can occur K1 ways, and a second event can occur K2 ways, and event 3 can occur K3 ways, ... and event N can occur Kn ways, then the total number of ways that all the events could occur in this particular sequence would be the product of all those individual ways. That's called the fundamental principle of counting. Okay. Permutation rule number 1, n permuted r ways, where order matters, is n factorial divided by n minus r factorial. Permutation rule 2, the permutation of n objects where you have identical objects, okay, occurring, like R1 object occurs, R1 ways. Then you're going to have to reduce the total number of permutations by dividing n factorial by the product of the repeated objects, if you will. Okay, because like I said, for the word Mississippi, if you interchange the 2 letter S's, okay, the first 2 letter S's, you still have the word Mississippi. So that's redundant, all right? You don't want to double count that, all right? And that's why we got to divide by this extra these extra factors in the denominator that represents the repeats to try to reduce the number of permutations so we don't double, triple, or quadruple count them. This is a combination formula where order does matter. Number of ways of choosing R things from N things if order does not matter. Okay, and this is the way to access the functions on your calculator. I already went over that. All right, ladies and gentlemen, let's see if we can go have some fun now in section 4.4. Now, we may not finish all of 4.4 today. I'm not concerned about that because 4.4 is probably going to spill over into next Monday, and we'll combine it with section 4.5 as we then use these counting rules or skills or tools to compute more complicated probabilities. So it don't matter really if 4.4 overlaps into 4.5, no big deal. All right, let's go into 4.4 and see if we can do a couple problems here at least. Okay, so learning how to count. Oh, wait a minute. This is 4.4. That's what I want here. Counting rules. Yeah, okay. And as always, it is nice to look at the examples, ladies and gentlemen. For instance, here's a good example here. There are 4 blood types that we discovered, A, B, and O. But blood types also have a race, I guess they call that what, rhesus factor, whether it's positive or negative, Rh positive, Rh negative. Finally, the blood donor can be classified either as male or female. How many different ways can a donor's blood be labeled? Well, Ladies and gentlemen, how many different ways does the blood types occur? There's 4 different ways for blood types, correct? A, B, and O. So there's 4 ways of blood types occurring, times how many different ways can the rhesus factor occur? 2, Rh positive or Rh negative, times how many different ways are the genders possible? Male and female, 2. So how many different ways or arrangements can we have for blood donors? That'd be 4 times 2 times 2 according to the fundamental principle of counting, which is going to give us 16 different ways. Do you agree? 16 different ways of having blood donors here, and they are all enumerated here. 16 different ways are enumerated in the rightmost column here, okay? You could have a type A positive male, a type A positive female, a type A negative male, type A negative female, type B positive male, type B positive female, type B negative male, etc., etc., etc. Everybody see that there? And again, the tree was pretty cool in helping us to see it visually. But, you know, to determine the number of ways that K1 and K2 and K3 objects can occur, you don't have to use a tree. You can just multiply, 4 times 2 times 2 to determine there's 16 possible ways. The tree comes in handy if you're trying to compute probabilities. Okay. In other words, what would be the probability of having a type O negative female blood donor? You would say what? What would be the probability of having a type O negative female blood donor? Well, how many ways can that occur? Only one way. 1 out of how many ways? 16. So that probability would be 1/16. Okay. What if I ask you this question? What's the probability of selecting a male blood donor? A male blood donor. Well, how many of these are male? There's a male, male, there's 2, 3, 4, 5, 6, 7, 8. There's 8 outcomes that have a male. So, ladies and gentlemen, the probability of selecting a male blood donor would be 8 divided by 16, or 1/2, or 50%, or 0.50. That makes sense. That stands to reason. You see that there? What would be the probability of selecting an Rh negative blood donor? Well, how many Rh negative outcomes are there in here? I see 1, 2, 3, 4, 5, 6, 7, 8. So there would be 8 out of 16, or 1/2, or 0.50, or 50% chance of selecting an Rh negative blood donor. All right. What's the probability of selecting an Rh negative male blood donor? Well, how many Rh negative male blood donors we have in here? There's 1, 2, 3, 4. I count 4. So that'd be 4/16, or 1/4, or 25% chance of selecting an Rh negative male blood donor. You see, so we can ask you a whole bunch of probabilities once you have this tree constructed and all the possible outcomes basically listed here. All right. Okay. Here's an interesting problem here, ladies and gentlemen, this example. The first year the state of Pennsylvania issued railroad memorial license plates. The plates had a picture of a steam engine followed by 4 digits. Assuming that repetitions are allowed, how many railroad memorial plates could be issued? Well, to do this problem here, you could think of the first mailbox is filled with a what? A steam engine. Do you agree? Steam engine. Then there's 4 digits. So there's 4 little mailboxes. Think of it that way. How many ways can we populate digits in the first mailbox? How many digits do we have to choose from? We have digits 1, 0, 1, 2, all the way up to what? Digit 9. Agree? Notice repetitions are allowed in our digits. So, ladies and gentlemen, to fill the first mailbox, how many ways can I fill the first mailbox with a digit?
10.
Well, yeah, 10 different ways. Times, how many different ways can the second mailbox be filled? Repetitions are allowed. 10. Times, the third mailbox can also be filled 10 ways. Times, the fourth mailbox can be filled 10 ways. So there would be 10 times 10 times 10, or 10 to the fourth, or 10,000. There would be 10,000, ladies and gentlemen. Different plates, number of plates that can be issued. 10,000. 10,000 unique plates that can be issued. Okay. Now, if you're in an area where there's more than 10,000 people that are going to be, buying into these plates here, you're going to have extra slots here to allow for the extra possible arrangements. In fact, in Pennsylvania, there was a huge demand, so they actually had to use letters to increase the number of arrangements or unique different license plates here. All right. Okay. Now, what if repetitions were not allowed? Well, to fill the first slot, there'd be 10 possible ways, but then you're going to keep a digit out for the first slot. So there would be only 9 ways to fill the second slot. But then you kept 2 digits out. So there's only 8 ways to populate the third slot. Times, and there'd be only 7 ways to populate the last slot. This is if repetitions are not allowed. And there would be less number of possible arrangements then, correct? All right. Let's see, any good examples here? A family has 4 children. How many different ways can they line up in a row for a photograph? Well, do you think order matters here? Order would matter, correct? And so this would be a permutation here. Example of a permutation where order matters. And so you could think of one way to enumerate the number of ways is think of having 4 spaces, four slots in which to line these people up. How many ways can I populate the first spot in line? That would be 4 ways. There's 4 children to select from. But I keep one of the children out to occupy the first slot. So that leaves me with 3 children to occupy second place in line. But now I have 2 people held out of the 4. So that leaves only 2 people left to occupy third place in line times 1 person left to choose for last place. There'd be 24 different ways of arranging these 4 people in line, first, second, third, and fourth in line. Okay, 24 different unique ways of arranging these 4 children in line. That's a permutation. Order matters. Okay. Example 444, a radio talk show host can select 3 of 6 special guests for the program. The order of appearances of the guests is important. Well, if the order is important, that means order matters. So in how many different ways can the guest be selected? Well, this would be a permutation because order does matter. So 6 permuted 3 ways. However you compute it, whether you want to, play around with the factorial notation or just use your NPR function on your calculator, there's 120 different ways of selecting 3 people from 6 in a specific order. A school musical director can select 2 musical plays to present next year. One play will be presented in the fall and one play will be presented in the spring. If the music director has 9 plays to pick from, how many different possibilities are there? Well, do you think order is important here? Well, it probably is important here because, we're going to choose a play to perform in the fall and then a second play to perform in the spring. And order does make a difference here, okay? Because of that, you should be thinking permutation. So we have 9 plays to select 2 from, where order does matter in how we select 2. That's a permutation. So there'd be 72 different ways of arranging 2 plays from 9 plays total, where the order in which they perform matters, fall versus spring, okay? All right, here's an example. How many permutations of the letters can be made from the word statistics? How many different unique ways can we arrange these letters in the word statistics to form a unique arrangement? Well, suppose that here is my first arrangement, statistics. Suppose my second arrangement interchanges these 2 T's. Would my word look any different for the second arrangement?
No.
No difference. And because of that, we would be double counting the word statistics as being unique, when in fact they're not unique. Because of that, liaison, because we have repeated letters in here, all right, we have to account for that. And therefore, we're going to have to use what they call the second permutation rule here. Namely, specifically, the S's repeat 3 times, T's repeat twice, the I's repeat twice, A repeats once, and the letter C repeats once. So, therefore, we have 10 letters total in the word statistics, 10 factorial, divided by 3 factorial, times 3 factorial, times 2 factorial, times 1 factorial, times 1 factorial. And when you go through and work this all out, using your calculator to help you out, we would discover that there's 50,400 unique arrangements, okay, of these letters in the word statistics. Can we come up with just one other arrangement for the word statistics here? Can anybody come up with a unique arrangement? Shouldn't be too difficult for the second one. By the time you get all the way up to 50,399, trying to come up with the last one would probably be a bear. But ladies and gentlemen, what do you think? Could I maybe go with like S, T, T, T? We accounted for all the T's. Maybe S, S, we accounted for all the S's. And then I, counted for all the I's. And then C, do you agree that would be a unique arrangement of these letters? It's different than the word statistics, correct? I'm not saying this is a word. I'm saying it's a unique arrangement. Do you agree? Isn't that a unique arrangement of these letters? How many more are there? Well, there's only 50,300 and what? 98 more? Anybody care to enumerate all those? We'd be here for a long time. But do you get the idea there? I showed you another unique arrangement. It has to be a unique arrangement. In other words, if you just interchange for like the third arrangement, if you just interchange these 2 T's and interchange these 2 S's, it'll still look like this arrangement here. That's not unique. You can't count that one. All right. So it has to be a unique arrangement. What would be another one here? Do you agree this would be a unique arrangement? TTT, SSS, IIC. Do you agree? That would be another unique arrangement of the letters in the word statistics. That's unique. And now there's only 50,397 more. Okay. It's easy in early going to, list some arrangements, but by the time you get down, get to around like 50,300 or whatever, trying to come up with the remaining arrangements would be extremely difficult. Imagine trying to sift through 50,300 arrangements. Yeah, that's happening. A computer system would be needed here to do this much quicker. Okay. Computers got us beat in two departments: perfect recall and speed. Humans cannot hold a candle to those two things. We got computers, ladies and gentlemen, that can do like 20 trillion calculations per every tick of the clock. 20 trillion. Could you do 20 trillion additions in 1 second? I couldn't even pick up my pencil in 1 second. All right. So computers are a marvelous device that helps speed things up that are otherwise literally impossible for humans to do accurately. All right, so these examples here are always good to look at, okay? Here's an example. The director of movies at the park must select 4 movies from a total of 10 movies to show on movie night at the park. How many different ways can the selections be made? Well, we will assume that order really doesn't matter. I mean, you're going to see 4 movies. Let's say the person stays for all 4 movies. You think the order in which the movies are presented really matters? Now, somebody could always argue, yeah, it does. Maybe, maybe the first 3 movies are horror movies and the last movie is like like a Barbie movie or something like that. And that way you won't go home terrified. You can sleep at night if you see the Barbie movie last, as opposed to seeing, a horror movie last. We'll assume generalize on that order does not matter here. If it doesn't, it's a combination. 10 in combination with 4. All right, so there'd be 210 different ways of choosing 4 movies from 10 movies if the order in which we select them does not matter, or the order in which we present them does not matter. All right, in a club, there are 7 women, 5 men. A committee of 3 women and 2 men is to be chosen. How many different possibilities are there? This is a little bit more complicated of a situation here as far as counting is concerned. I got a question for you, ladies and gentlemen. In between this event here, a committee of 3 women, and in between the event, 2 men, what word do we see in between these 2 events? We see the word and. And suggests the multiplication rule. Multiplication rule. So, ladies and gentlemen, how many different ways, first of all, let's work on the first event. How many different ways can the first event occur? In other words, how many different ways can I choose 3 women from 7 women if order does not matter? Do you agree? That would be 7 in combination with 3. How many different ways can the second event occur? In other words, choosing 2 men from 5 men. Well, how many ways can I choose 2 men from 5 men if order does not matter? That's 5 in combination with 2. But the fundamental principle of counting says I multiply these together, because there's 7 in combination with 3 ways of the first event occurring, and there's 5 in combination with 2 ways of the second event occurring. So to compute the total number of ways of these occurring in a particular sequence, we multiply the individual number of ways together. And therefore, when you do this on your calculator, you would have 350. Now, another way we could have done that on our calculator without using this laborious factorial notation is I could have done it this way. I could have said 7 in combination with 3. You know what? For safety, I'm going to put it inside parentheses. 7 in combination with 3. Whoops. Hold on a second here. Wait a minute. times, open parenthesis, 5 in combination with 2. And we get 350. Everybody see that there? That's quicker than using this factorial notation. You can use the factorial notation if you want, but you don't need to. You can speed it up just by using the NCR function. All right, 350 different ways of choosing what was it? 3 women from 7 women and 2 men from 5 men. Okay, if order does not matter in how we choose the women and the men from the respective lots. 350 different ways. And here's just a recap of the counting rules that we've learned. The fundamental principle of counting, permutation rule number 1, permutation rule number 2, if you have repeats, and the combination rule there. All right. All right, ladies and gentlemen, I want you to do for classwork number, where did we leave off? Anybody remember? Was it classwork 2 or?
This will be classwork 3.
Okay. We can open up a running tab on classwork 3. I want you to do problem number 1 here. Throw this into classwork 3. How many 5-digit zip codes are possible if digits can be repeated? And then do the problem over again if you cannot have repetitions in the digits. Go ahead and do that problem. Call that classwork number 3 there. Okay, first question. How many 5-digit zip codes are possible if digits can be repeated? Well, you can think of this as being like 5 little mailboxes, 2, 3, 4, 5. And we can populate each mailbox with digits from 0 to 9. So how many different ways can the first mailbox occur? Or this first event occur, which is the first mailbox? We can populate the first mailbox with 10 digits, correct? Now notice digits are repeated. So there's 10 digits that can populate the second slot of our 5-digit zip code. 10 digits to populate the third slot. Times 10 digits to populate the fourth slot. Times 10 digits to populate the fifth slot. So you know what? There's 10 to the 5th power. And 10 to the 5th power is really what? 100,000? There's 100,000 different zip codes that you can form. Okay, 100,000 different zip codes you can form if digits are allowed to repeat. One possible zip code would be the zip code 11111. Do you agree? That's a possibility. Another one is 00000. There's 100,000 of those. There's 100,000 unique zip codes of 5 digits if digits are allowed to repeat. Suppose there cannot be any repetitions. Well, think of your 5 slots again. There's 10 ways to populate the first digit of our zip code, but we got to leave one of those digits out now. So there's only 9 digits left to select to populate the second digit of our zip code. Times, but now we leave out 2 digits, one for the first and the second position of our zip code. Well, that leaves only 8 digits to select to populate the third slot. But now we left out 3 digits, so that leaves only 7 left to populate the fourth slot. But now we left out 4 digits, so that leaves only 6 digits to populate the what? The fifth and final slot. Multiply those together, and what do you get? Anybody multiply all that out? 10 times 9 times 8 times 7 times 6?
30,240.
Okay, so there's 30,240 different ways of forming a unique 5-digit zip code if repetitions are not allowed. Not allowed. No repetitions are allowed. So one answer could be, you know, like, hey, here is one zip code. Do you agree? No, that isn't. You could have 0, 9, 8, 7, 6. That's one possible zip code, correct? What would be another one where repetitions are not allowed? Well, 9, 8, 6, 7. Isn't that unique? Wait a minute. 9, 8. I'll put 0 in here. 98607. That's another unique zip code, correct? So there would be 30,240 of those. Why do you think there's less if repetitions are not allowed versus if the repetitions are allowed? I mean, just kind of obvious why there would be less. Do you agree? Because repetitions are not allowed. So, like, you cannot count this one for the second question that's being asked. That's not allowed. So there's going to be less. All right. All right, classwork 3. I want you to also throw this one in here. Number 3, do this one. This will also be part of classwork 3. Go ahead and do that one now. So it says 7 elementary students are selected to give a 3-minute presentation on what they did during the summer vacation. How many different ways can the speakers be arranged? How many different ways can these 7 speakers speak in a particular order? Okay, go ahead and figure that out. All right, ladies and gentlemen, do you think order matters here?
Yes.
All right, order does matter. So this is going to be a permutation or combination. What do you think? it's going to be a permutation, correct? All right. Now, there's a couple different ways you can compute this here. You can have like 7 spots. First to give the speech, second to give the speech, third to give the speech, fourth to give the speech, fifth to give the speech, sixth in line to give the speech, and seventh in line to give the speech. All right. How many ways can we choose from our 7 students to go first in giving their speech? There's 7 ways. Do you agree? 7 students to choose for, doing the speech first. But one of them is going to do the speech first. So we keep that one person out. So we only have how many ways or how many students left that can go second? Give the speech second. Give the speech second would be what? 6 ways, correct? But now a student went first and a student went second. That means we only have 5 ways left, 5 students left to select who can go third. But now 3 students have gone and given their speech. So we only have 4 students left to choose as to who's going to go in fourth place. But now 4 students have gone, first, second, third, and fourth. We only have 3 students left to choose who's going to go what? Fifth. And there will be 2 students left to determine who goes what? Sixth. And then 1 student left to determine who goes last. All right, when you multiply all these together, what do you get? Anybody multiply all those together?
5,040.
All right. So there's 5,040 different ways, ladies and gentlemen, in which these people can deliver the speech in a particular order. Okay, that's one way to do the problem. Did anybody use the permutation function to do the problem? Just curious. Notice this is equal to 7 factorial, by the way. Isn't that 7 factorial? What we just computed there. Another way, ladies and gentlemen, let's think of it this way. Order matters. So we got 7 students to choose from. And we're going to choose how many of the 7 students are we going to choose? We're going to choose 7 students where order matters. So how many different ways can I choose from 7 students to go in a particular order in giving a speech? When you work this out on your calculator, you're also going to get to 5,040. 5,040. That's another way you could have maybe done the problem, okay? These are both equivalent ways. In fact, these are equal to each other. I'll let you know a little secret, ladies and gentlemen. This is always true. N permuted n ways. N permuted n ways is always equal to n what? Factorial. Everybody see that there? N permuted n ways is n factorial. That's always true. Don't believe me? Let's look at the formula. N permuted n ways is by the formula, n factorial, divided by n minus n factorial. So this is going to be n factorial. Now what's n minus n? That's 0. But what's 0 factorial? Careful, 0 factorial is not 0. It's 1. So this is n factorial over 1. We've just kind of proved it to ourselves. Okay, this is n factorial. All right, any questions about that problem there? All right, I got a question for you here. I'm going to make a problem up. If I have the word Abe, A-B-E, how many unique ways can I arrange these 3 letters? How many unique different ways can I arrange these 3 letters? Anybody? How would we determine a number of ways?
I multiply the ways you can put each letter in each slot.
That's right. Yeah, you can think of it as being like 3 slots. First slot, second slot, third slot. How many ways can we populate the first slot with one of these letters? Well, we got 3 letters to choose from, correct? But we leave one of the letters in the first slot. That means we only got 2 letters left to populate the second slot. But now we left out 2 letters times we only got 1 letter to occupy the last slot. Oh, 3 times 2 times 1. Isn't that better known as 3 factorial? Isn't that better known, ladies and gentlemen, based on what I just showed you, as 3 permuted what? 3 ways? Isn't that true? Order matters here. So how many ways are there? What is 3 times 2 times 1?
6.
There's 6 ways. Here's what I want you to do now. For classwork number 3, throw this into the pot. I want you to enumerate all 6 different unique arrangements of these letters. Go ahead. All 6 unique arrangements, different arrangements for those letters. There's 6 of them. Okay? See if you can enumerate them all. This one's doable. All right. How many ways are there? How many different unique arrangements are there? There should be 6, right? Well, ABE, BEA, EAB, BAE, EBA, and AEB. Did anybody get anyone?
Yep.
Okay. Now this was a pretty easy problem because there are only 6 arrangements, correct? Could you imagine? Let's see here. How many different arrangements could you have for these letters here? Well, you got how many different letters? 1, 2, 3, 4, 5, 6, 7, right? 7 different letters. So you could think of it as like 7 different mailboxes here. 2, 3, 4, 5, 6, 7. 7 ways to populate the first letter. 6 ways for the second, 5 ways for this one, 4 ways for this one, 3 ways for this one, 2 ways for this one, 1 way for this one. This is better known as 7 factorial. Or this would be another way of saying 1, 2, 3, 4, 5, 6. This would be a 7 permuted 7 ways, correct? Or, ladies and gentlemen, you agree this is saying the same thing as, check this out, 7 factorial divided by 1 factorial times 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 1 factorial. Where did this rule come from? What is it? Remember we seen that one? That rule was a permutation rule used if we had what? Repetitions. Do you agree? But why don't we need to use this rule in this case? In this case, it's what? Not really necessary because all the letters repeat what? Uniquely one time. So this collapses down to 7 factorial, which is 7 permuted 7 ways. All right. Now, what is 7 factorial? Well, that's 7 times 6 times 5 times 4 times 3 times 2 times 1. That's going to be a pretty large number. Anybody dial it up for me?
5,040.
5,040. Could you imagine? Look, we probably even struggled a little bit in just doing 6 different enumerations. Could you imagine trying to arrange these letters in a unique order? 5,040 different ways? Can you imagine doing that problem manually? Not only would it take a tremendous amount of time, but stop and think of how inaccurate we would be and how many errors we would make. Imagine sifting through like 5,000 of your arrangements to see which ones you got left. Talk about difficult. A computer could do this problem within a fraction of 1 second. Boom, done. List them all. All right, so how do we get on that topic there? Okay. All right, so what we're doing is we're looking at permutations here, okay? Now here's an interesting one. Throw this into the pot for your classwork. Number 7, this will also be part of classwork 3. 4 8-sided dice are rolled. How many different outcomes are there? 4 8-sided dice. So we'll assume that these dice have, these die have 8 sides to them, like 1, 2, 3, 4, 5, 6, 7, 8, with the numbers 1, 2, 3, 4, 5, 6, 7, 8 on. Okay, go ahead and try to enumerate how many different outcomes are there. You don't have to actually, I just want to know how many different outcomes there are possible. You don't have to enumerate all the outcomes. That would be virtually impossible. Okay, do number 7, part of classwork 3. Okay, let's take a look at this problem here. We have 4 of these 8-sided die. All right, how many different ways can I roll the first die? 8 possible outcomes, do you agree? How many ways can a second event occur? Rolling the second die. 8 possible ways. Times, how many ways can we roll the third die? 8 ways. Times, how many ways can the fourth event occur? We roll the fourth die 8 times. This will be 8 to the 4th power. And what is 8 to the 4th power? So we use our fundamental principle of counting. So 8 to the 4th power is that 4,096? 4,096 different ways. Now, if you wanted to enumerate all these outcomes, these 4,096 different outcomes, one way to do it is you could build a tree. Die 1, you could roll what? 1 of 8 outcomes, correct? So you'd have 8 branches.
I know.
You could roll a 1, a 0, not a 0, a 1, a 2, 3.
I've been sitting here messing around with the different
6,
N types.
8.
And I do this. I love to do this.
Okay. Now, from each of these branches would be what would emanate 8 more branches for die 2. So each of these branches would have 8 more branches emanating from it. Starting to get the idea here. Imagine trying to draw this tree. And then from each of the end of these, there would be what? 8 more branches emanating from each of these. And then from the end of these, for the fourth die, there'd be 8 more branches emanating from the end of each of these. Talk about a very, very difficult problem, if not impossible, literally impossible to draw a tree diagram here, ladies and gentlemen. Okay. So that's not happening. But luckily, we're not asked to enumerate all the outcomes. We're just basically just asked to determine how many outcomes there would be. That's the good news. All right. Still with classwork number 3. I want you to do problem number 8. Number 8. The call letters of a radio station must have 4 letters. The first letter must be a K or a W. How many different station call letters can be made if repetitions are not allowed, if repetitions are allowed? Now, we will assume that there's only uppercase letters in the call sign of the station. No lowercase letters, all uppercase letters. Go ahead and do problem number 8. This is also part of classwork number 3. the call sign of the station must begin with the letter K or the letter W here. And there must be 4 letters in the call sign. If repetitions are not allowed, that means we have 26 ways to populate the second slot of the call sign. There's 26 uppercase letters in the alphabet, but we leave one of the letters out here. But this is not right. What's wrong with this? Right off the bat, I made a mistake. What is wrong?
A or W can't repeat.
That's right. Look at, we left K out already, didn't we? So this should not be 26. No, we only have how many letters to select for the next call letter here? Should only be what, 25 here, shouldn't there? We already left K out. Times, there's only 24 letters left for this slot. That's not correct. Times, there's 23 letters less for the 4th and final slot. This should also be the same thing here. This should be 25 times 24 times 23. Now, or means we do what? What does or mean? Or means we add. Do you agree? So we got to add this number of possible ways of a call sign where the call sign begins with a K to the number of possible call signs where the call sign begins with a W. These are not correct here. All right, so what is 25 times 24 times 23? $13,800. So there's 13,800 different call signs that begin with K, and there's 13,800 different call signs that begin with the letter W. Add those together, and totally there would be 27,600 different call signs that either begin with the letter K or W, totally. Okay. Now, this is not correct because we leave one of the letters out of our alphabet, namely K. That means we have 25 letters to select from to populate the last 3 letters of our call sign, where repetitions are allowed. So therefore, this would be 25 times 25 times 25. Likewise, if our call sign begins with the letter W, there is 25 times 25 times 25 different call signs where repetitions are allowed. So that's 25 times itself 3 times, or 25 to the 3rd power, which is 15,625 different call signs that begin with the letter K where repetitions are allowed with letters. Likewise, also 15,625 call signs beginning with the letter W where repetitions are allowed. So adding those together, there would be 31,250 different call signs that either begin with the letter K or W where repetitions are allowed here. So in other words, one call sign could be what? You could have the radio station or the television station KK, K, K. Do you agree? This is station KKKK, or this is station quad K or something, you know. That's one, right? And there's 15,624 more of these arrangements. Okay. All right. Okay, so we got to stop here. We're out of time. But what we did is we investigated kind of deeply permutations here where order kind of matters here. You know, when we come back on Monday, we'll finish up this section, focusing more so on combinations where order does not matter. And then we'll wrap up this chapter by looking at how to compute probabilities of compound events, more complicated events, which are going to need our counting tools that we have put in our toolbox here today. So I will stay on the line.